Welcome everybody to my channel, and in today's tutorial talk about interaction between Vellum grain and balloon inflation pressure. So this is the end result. So the balloon is inflating and pushing the sands away, and the inflation is controlled by time, and it's custom modified. So we'll go through the HIP file and scene file and see how it was built. The scene file will be available in my Patreon, so please support me on YouTube by subscribe, comment and share, and participate in my Patreon, where you will find a lot of scene file. So this is my Patreon page. You will find a lot of already made HIP files that's connected to YouTube. These are the new and the previous setup, so it will be very much appreciated if you support me over there. Thank you. So this is my scene file, couple of cameras movement, and it was rendered in Redshift. So let's go here. Where do we start? Always we start from the box. So I started with simple box. I remesh it, so I have higher density and triangle, and then I added a group for the whole area. I call it all. And then I added another group just for the points that's supposed to be at the bottom, but it's not updated. So let's do it quickly. Let's go perspective, set view, bottom. Here's the bottom, and I will select. So the bin is selected. I will select this one, and I will remove the eye, and I want box selection, select the whole area, press enter, Alt 1. So now it's selected again. Okay. After that, I want to run the Vellum simulation for the pressure, the balloon for this area. Okay. So I added a Vellum cloth. I'm running it all, the group all, and set uniform density 0.1 and thickness of 0.25. I give it a high stiffness for the stretch, call it stretch group, and very low bend stiffness. Then I run a Vellum constraint for the pressure. So here it is pressure. The stiffness I kept it very low at 10, and stiffness drop off is increasing of 0.5, and I call the group pressure. Then I run a bin to target for the group that's at the bottom, and it's soft constraint, and just the value of 1000. Then I went to the Vellum solver. Just give it a second. Now it's reacting. There is a ground, substep of 4, and this is the RAM. Okay. Now if I run it, it will just inflate to this pressure of wrist length of 1. But I want to control the inflation area, that I want it to move from here to here. Okay, gradually. So what I did, you remember the box? So each box always need a sphere, so this is the sphere. Okay, so we have a sphere. Let me template the box and the sphere. See, I transform it to the middle. I give it the infamous red color, so we have value in CDX of 1, and I want it to travel along the box, so I draw a curve that's reference the geometry. So draw a curve, and in the projection geometry, so I have this line like this. Then I carve it. As you can see, this is the point. Whee! And in the curve I extract the point. Okay, so extract the point and I animate it from 0 to 1 on the timeline, so it's moving. So I have a point and I have a sphere that I want to be traveling, so it's a copy to point node. Now the point is traveling. I animated the scale for extra effect, so this one is animated like this. I remap the CD, the red color, I call it MM, and I change the range from 0 to 1 to be 1 to 5. Then I took the remesh geometry before it was running through the simulation. I created the MM attribute there. I give it a value of 1. Then I transfer it. Let's visualize the MM. So in the transfer attribute, this is the MM. So this is what will drive the inflation. Okay, then I give it a little bit more blur. So it become more soft, and I added a null for the output. This null will have the MM point attribute. Now back to the Vellum solver. Let's dive in. Here in the force, I added Vellum constraint property, and in the Vellum constraint property I want the attribute in the null object to be read out and ingested during the simulation phase. So in the Vellum constraint property, you go to the input, choose one of these empty input. I choose the third one, the sub, and I point it to that null. Here I left everything as is, but here in the binding it's constraint geometry, so you are affecting the constraint. Here I'm affecting the stretch group and the pressure group, and I want to play with the wrist length scale, so I activate it. Also you can activate the stiffness if you want to play with it like this. I think I was activating it. Here I want to read the MM parameter. I think here in the constraint you cannot you cannot create attribute, just what you call it, variable like float. See, so it's inside the node. So MM float, I'm reading from the second input, the one we put the null in, and I want to read the MM from each point. So now it's stored in this float. I want the wrist scale to read the MM. You remember, wherever there is no sphere, it's 1. With the sphere, it will increase up to 5. So I'm just directly reading it, and I am playing with the stiffness that I'm dividing it by 10. Here I'm just telling if the stiffness is more than which like yeah, because I've divided by that, this will never be evaluated, because I make sure here it's always below. Then I added a Vellum process, post process, so some spatial blur and cutmal and passes of 5. Then it was saved. Saved. What we like to see here? Okay, let's play it. So it's very much erratic. So it didn't inflate all the way. It's just following that sphere. It go back to 1. Cool. So after I finish this part, I went to the second part of the grain. So as you can see, I separated both of them, because if you look at it, you want the balloon to affect the grain, but the grain is not affecting the balloon. So better to separate to save simulation time. So here I had to create a bound. I transform it bigger. Then I Boolean. Now I excluded the area of the balloon, so I'm surrounding it with this box that will be converted to grain. I call it sand, and I added Vellum constraint grain. So here it is, and it's open at the bottom, so this is where the bag will be, so there is no intersection. And this is the what's this? This is the box for collision. Particle size 0.5. A blade with the attribute noise of the attraction weight. So let's view the attraction weight here. So attraction weight, I created it and I give it a value between 0.01 and 1. And the blade with the fractal noise and the offset and the element size. So this is how it looks. Then I added a Vellum glue with increased maximum surge and 1 million stiffness and high damping ratio, so it will not flicker. The Vellum solver, sub-step of 4, and here I created a Vellum attach that will be attached to that balloon which will inflate. So it's running and being evaluated and creating this attachment every frame. So it's attached to geometry. The bones, that's the sand that we created, and we are attaching to the grid, the box, the balloon, with a maximum distance of 0.1, stiffness of 100,000, and some damping ratio. I added a pop speed limit of 30, but you don't need this node because in the Vellum solver advance the motion already it's locked at 30. Then I save it. Let's save it like it's 5 million. So just choose a frame somewhere in the middle. So it's clumping wherever it's red, and it's loose wherever it is one or blue. Take another frame. See, it's not just each point separated by itself. We have some thickness here. See, like if I remove this one, you can see some wet and some dry sands together. let's go here. After that, I give it a color according to the weight attraction, so it will be visualized more. So wherever it's dark, it's very loose. Like if I move here, you'll see this part fall down more. See, the attraction weight is very low, so they fall down. Wherever it's rigid, it remains, as you can see here. So the dark area, they are more scattered, and the other area they clump together more. And after that, I run the render. So this is how it looks, with some depth of field. So once again, thank you very much for your continuous support, and expect to see you in my membership on YouTube and to participate in my Patreon, so I'll be able to add more and more tutorial and cool Houdini stuff. Thank you very much. Have a nice day.